Well, it is a pleasure to have Nuno Cardoso from the University of Miami, and he will be speaking about stability conditions on products of Kronecker quivers.
Thank you very much for the invitation. It's a pleasure to be here again in Mexico. I'm always very welcome, see old friends reunited. And as he said today, this talk will be mainly about bridgeland stability conditions. And the main objective is to study products of Kronecker quivers, but this is still a work in progress. It's not done yet, so don't get your hopes really high. It seems quite hard, the problem, but I will sketch more or less what we'll be doing today. The talk will be divided in 4 halves, in 4 parts. The first one will be a small motivation coming from physics. Then we will see some precise definitions. A lot of people talked about stability conditions right now, so I believe since I'm the only student among them, I believe it's my job to give like the basic definition. Then we'll see some examples, and at the end the open problems we are working on. So the motivation is as following. This, the first paragraph, everyone quotes this from the paper by Bridgeland. So it was introduced by Bridgeland, motivated by the work of Michael Douglas on pi stability for D-branes in string theory. And let me sketch a little bit the physical situation. The main point here is not to understand everything what's going on, but just how they behave. So we start with n equals to superconformal field theory, and associated to this theory we get 2 topological twists called the A model and the B model. These are topological conformal field theories. The first one, we do not have a precise mathematical definition yet, but these topological conformal field theories should be understood mathematically as A infinity categories. So if we consider all superconformal field theories up to isomorphism, we get a moduli space, and this is expected to be a reasonably well-behaved complex space, let's say a complex orbifold, and sitting over it, there is a much better behaved space, which physicists call the Teichmüller space, consisting of superconformal field theories plus some sort of framing. So you should view this as like the classical picture of the Teichmüller space and the Riemann moduli. So and the hope is that this n is a complex manifold with a discrete group action whose quotient is m. And at general points, we have 2 foliations of M. We can either fix the A model or the B model of our theory. So that's the general picture. Let's move on to the interesting case for us. So we start with a Calabi-Yau threefold. So I'm denoting by I the complex structure, and this beta plus I omega complexified Kähler class, where beta is the B field. And physicists have a way to associate to it a superconformal field theory called the nonlinear sigma model on X. So as before, we have again 2 topological field theories associated, the A model and the B model. And if we understand them in terms of A infinity categories, on the A side we should have the Fukaya category given by this X and this form, and on the B side we should have an enhanced version of the derived category of coherent sheaves on X. So and this part is important. The sigma model construction should give an open subset of the moduli of superconformal field theories. So in for X simply connected, we expect that the leaves in M, in this case those 2 leaves which we have fixed in the A model and the B model, in this case should be given as following. Suppose you fix the A model. So in this case it would be we would get as the leaves the space of complex structures on X up to diffeomorphism. So we would change only the B side. And if we do the opposite, we fix the complex structure on X and we change the A side, we should get what's called by physicists the stringy Kähler moduli space. And up to now we have no precise mathematical definition of this space, but if you believe mirror symmetry, you can see it as the moduli of complex structures on the mirror of X. And one of the main points of this Bridgeland stabilities is like, let's say in 20 years, we'll be able to give a definition of this space using these stability conditions, a precise mathematical definition. Up to now, everything is a conjecture, like it's a big picture, but that's the hope. So here is what we have. We consider that's Bridgeland's idea, and based on what Teichmüller did for the Riemann moduli problem. We start with the moduli of curves, and you have a space sitting over it, the Teichmüller space, and we can view the moduli as the quotient of the Teichmüller space by the mapping class group, right? So here let's try to do the same. Analyzing we start with any triangulated category. Let's say we need some mild hypothesis for these claims to be true. So we define this a space of stability conditions on D, which becomes a complex manifold. And we have two natural actions, one by the group of autoequivalents of D on the left, and this one should correspond to the discrete group action on N, given M as the quotient. And we have a free C action on the right. So these two actions we have. And here is the expectation. This is like a huge open problem. It's still way beyond of what we want. The expectation is that when you pick D as the derived category of our Calabi-Yau threefold, we can embed this string Kähler moduli space inside this double quotient of the space of stability conditions by the group of autoequivalences and by C. And similarly, we have a mirror statement. If we take D as the Fukaya category, we should be able to embed the moduli of complex structures on this double quotient. But as I've said before, this is way beyond our understanding right now. For example, if you have a compact Calabi-Yau threefold, we don't even know if the space of stability conditions of the derived category is empty or not. This is still an open problem. So up to now, we are in that level of understanding. So we still do not know if it's empty or not. So you see, to prove this, something along these lines will take 10 or 20 years. So let's move on to some precise definitions, but that's the main picture. There's a huge area in mathematics and physics which will come as soon as we understand better these stability conditions. There are several conjectures. So if we are analyzing carefully the physical definition, Bridgeland proposed the following. Some people believe we still need to refine it a little bit, but that's what we have for now. Let's start with any triangulated category, and a stability condition on D will consist of a pair Z and P, where dZ is a group homomorphism coming from the Grothendieck group of D to C, called the central charge, and this P is a family of full additive subcategories of D indexed by real numbers. So you should think of these P phi's as semi-stable objects with phase phi. So more or less like slope phi. Remember, in the case of vector bundles, you have like these semi-stable objects with the slope mu. In that case, it's mu, but here is phi. We prefer phi. And this is indexed by real numbers just because we have a triangulated category instead of an abelian categories. And satisfying the following axioms. The first one is that this should deserve the name of phase. It says the following. You have like this semi-stable object, E, and when we apply the central charge to this object, we get a complex number where the argument is pi phi. So that's why this is like the phase of the object. We have some compatibility with translations. When we translate these subcategories, we just add +1 on the phases. We have some orthogonality property. There are no homomorphisms between semi-stable objects when the phase of the first one is greater than the phase of the second. And finally, the most important one is what's so-called, today we saw a lot of it, the Harder-Narasimhan filtrations. So this is given, you consider a non-zero object in D, so we require that there will be a collection of triangles like this, where each Aj is semi-stable, non-zero semi-stable, and we have decreasing phases. So you should think of this line as a filtration of E. It can be we can make it precise. We view this as a filtration, and these Aj's are the semi-stable quotients. They inspired by the case of curves. That's the name Harder-Nard's-Simon. And we will denote by stub of D the set of stability conditions on D. Consider all of them. How much time do I have?
You have 15 minutes.
So this is the main axiom, and let me mention that under all of the other axioms, this filtration is unique. You just need to require these objects to be non-zero. Some people forget it in their papers, but that's what we need to require. So, and the main theorem by Bridgeland is the following. The space of stability conditions has the structure of a complex manifold. This, more or less, as I'm stating, is wrong. But we need to add, as Gabriel mentioned before, in that list of axioms, the so-called support property by Kontsevich and Zeuberman, or the local finiteness by Bridgeland. We need that axiom, and we also need that to get a finite dimensional space, we also need that the Grothendieck group is finitely generated. But you know that in practice, let's say you consider an elliptic curve, the Grothendieck group is not finitely generated. So what you do, you work with a quotient of this group, which is finitely generated. So you replace the definition of the Bridgeland stability instead of the Grothendieck group, you consider some finitely generated quotient. So up to these adjustments, you will indeed get a complex manifold. But these are the technical part. The main important are those. And we have some natural actions on this space of stability conditions. First of all, as I've said before, we can act by autoequivalences of D on the left. So you have an autoequivalence of your category. It induces an isomorphism on Grothendieck groups. So we have our central charge. Since we want a left action, we can just compose that with F inverse. And to change the categorical part, the phases, we just apply the functorial to that subcategory. And similarly, we have an action of this universal covering space of the orientation preserving isomorphisms. So this action is very easy to define. You just need a convenient way to describe this space. So the easiest one, an element here can be viewed as a pair, where the first is a orientation preserving isomorphism. So use this to change the central charge. You compose, you have something to see. Then you compose with this orientation preserving. And the second bit of information is a function from R to R, which is increasing, and that we use to change the phases. So that's why we need this universal covering space, because we need this function to change the phases. Otherwise, the action wouldn't be able to be defined. And since we can view C as a subgroup of this universal covering space, we also get an induced action of C on the space of stability conditions. And this one is always free. So now let's move on to some examples. When you consider curves, let's say smooth projective, then there will always be a stability condition on this derived category whose central charge is given by minus the degree of E plus I rank of E. This is more or less in spirit the slope stability. And it was proved by Bridgeland and Macri that the action of this group on the space of stability conditions is simply transitive, so we get this isomorphism. And it can be proved that this group is isomorphic to C times the upper half plane. This H is the upper half plane. For the case of Gino 0, it was proved by Okada that the space of stability conditions is isomorphic to C2. And this relied on a careful analysis of exceptional collections on P1. So and one of the main players also is given by quivers. Sometimes they are related, the geometrical part and the quiver part. So we start with a finite dimensional algebra over a field K. So in this case, it's easier to give stability conditions because the category of representations is of finite length. So that Harder-Nard's-Simon filtration, which is harder to check in practice, in this case will be automatic. So we can always give central charge like this. We just add the dimension on the second part, on the imaginary part, and we can consider any group homomorphism between the Grothendieck group as the first part. So we always have stability conditions with central charge like this. So, and for us, the main point, the main theorem in this case of quivers was proved a year ago by Dimitrov and Katsarkov. They've been updating the paper so much and adding a lot of results, but this part was from a year ago, that when we consider the Kronecker quiver with any arrows, the space of stability condition is isomorphic to C times the upper half plane for all n greater or equal to 3. The cases where n is equal to 1 or 2 were proved before by King and Okada, and these are isomorphic to C2. So this one is like the same as when you consider P1, because if you remember, there's a derived equivalence between the derived category of P1 and the representations of this quiver by the work of Beilinson. And finally, we have these open problems. How many minutes? 5. So I believe we have plenty of time. So here are some open problems we've been thinking. The first one is of a general nature. Is how connected is the space of stability conditions. You know that the Teichmüller space is always contractible. And in all computed examples, and in all examples we know the space of stability conditions is always contractible. But in practice, for example, the case of K3s dealt by Bridgeland, or the case of quadratic differentials by Ivan Smith and Bridgeland, and also by Fabian Hayden, Katsarkov, Kontsevich. We need to work with a connected component of this space just because we cannot prove it's connected. We give a precise stability condition, but we need to use some connectedness hypothesis, so we need to restrict to the connected component. But we believe this is connected in all those cases, but we cannot prove. But as soon as you prove something along these lines, we get non-trivial implications for the group of autoequivalences of the derived category. This is something that will have non-trivial consequences. So this we are thinking in some cases of quivers related, but it's not the main point. The main point for us will be 3. Also, we ask the question, can we compute the space of stability conditions for Pn when n is greater or equal to 2? This doesn't seem to be so easy, but I'm mentioning because when you compute the space of stability conditions for the Kronecker quiver, in reality, we are computing this space for the non-commutative projective space in the work of Kontsevich and Rosenberg. So in that case, the quiver associated with the non-commutative projective space is like the Kronecker quiver. But in this case, the quiver we get associated is given by the Beilinson quiver, which is much more difficult and has relations. So in this case, it's not so easy. Even for P2, some people believe it can be proved, but up to now, there is no complete description of this space, a global description. But here is like the point which is important for us. We want to analyze the space of stability conditions for a product of Kronecker quivers. So we believe, I won't state this as a conjecture because my advisor wouldn't allow me to do so, but we believe this space of stability conditions is given by the product of these two spaces. And here is just a remark, the dimensions agree, so we are not doing something really stupid. So the dimension is counted by the number of vertices here, so we have 2 times 2, and here we have 4. So it agrees. So for example, just to make sure you understand this product of quivers, because there are 1 million ways of defining products of graphs and directed graphs. So the product we are considering is the following. If we have the Kronecker quiver with just one arrow, and take the product, we should get this acyclic square. So in this case, we would get C4 as our space. For this quiver here, much more complicated, right? We expect to get C3 times the upper half plane. And this problem may not seem so interesting, but this is just a part of a general theory. These Kronecker quivers, in a non-commutative version of Galois theory they are developing, should play an important role. And this is all related to perverse sheaves of categories, which after, let's say, a lot of years, a long time, we expect to have applications to rationality problems. So some interesting geometric applications. So let's say in the end, the hope would be to prove the non-rationality of the cubic fourfold, let's say the dream of this project. And finally, this is a little bit harder. We need to formulate it properly also. We would like to analyze the space of stability conditions of this Kronecker quiver with coefficients in these Kronecker quivers. To understand what we want, let's fix m equals 2 and n equals 3. So the representations we want to consider are the following. We replace the vector spaces by these derived categories of the quiver over here. And instead of vector spaces, we consider exact functors. So this should be our representation. So what we would like is to cook up a triangulated category from this, define the space of stability conditions, and then analyze it. And as you can see, these categories are really complicated. But it seems that this space will have interest in wall crossing, and maybe the question we ask is, can we get new identities for Jacob forms in this space? I believe that was all for today. Thank you for your attention.
Any questions?
Yeah, this slide. So the first thing should be more or less trivial to check because this product is just equivalent to 4.
Yes.
So it's potentially finite. So it should be an easy exercise. But in general, it seems too naive. I mean,
The conjecture. We can talk later about this. It's interesting. I would like to see more about this. Actually, I need to ask you some questions.
More questions, anyone? Well, thank you very much, Nuno. And so, we in 20 minutes in the beach across